Wait a minute, how did we end up here? Let's travel back in time to find this out. When we think of an artificial black hole, the first thought that strikes on our mind is a particle accelerator, and exactly that's what we are going to discuss now.
Welcome everyone. We are Team Flash and going to discuss about particle accelerator, its types, working principle, and some interesting facts. Moving to next slide, let me give a brief introduction regarding particle accelerator. Particle accelerator is a machine that uses electromagnetic fields to propel charged particles to very high speeds and energies and to contain them in well-defined beams. Large accelerators are used for basic research in particle physics. It can accelerate two beams of protons to an energy of 6.5 and cause them to collide head-on, creating center of mass energies. Accelerators are also used as synchrotron light sources for the study of condensed matter physics. This operation is only to run beams. Synchrotron light is extremely intense, hundreds of thousands of times more intense than that of conventional X-ray tubes, and highly collimated. Synchrotron light is emitted with energies ranging from infrared light to hard X-rays. In the upcoming slide, we are going to discuss the type of possible accelerators. Particle accelerator in electromagnetic uses changing magnetic fields to accelerate particles. Since these particles pass through same accelerating field multiple times, the output energy is not limited by the strength of the accelerating field. Particle accelerator in electrostatic uses static electric field to accelerate particles. Common types are Cockcroft-Walton generator, Van de Graaff generator. Accelerating voltage is used for determining kinetic energy. Since our main focus is on electromagnetic or electrodynamic particle accelerator, from this slide we will discuss about its types and working principle. Electrodynamic particle accelerator. Due to the high voltage ceiling imposed by electric discharge, in order to accelerate particles to higher energies, techniques involving dynamic field rather than static field are used. Magnetic induction accelerator. Accelerate particles by induction from an increasing magnetic field, that is, circulates electric field which can be configured to accelerate the particles. Linear accelerator. Particles are accelerated in a straight line with a target of interest at one end. Cyclic RF accelerator. Particles move in a circle until they reach sufficient energy. The particle track is typically bent into a circle using electromagnets. Magnetic induction accelerator. There are two types. Linear induction accelerators. They utilize ferrite-loaded non-resonant induction cavities. Each cavity contains two large washer-shaped discs with ferrite toroid inside connected by an outer cylindrical tube. Betatrons. It is a circular magnetic induction accelerator invented by Donald Kress in 1940. These machines, like synchrotrons, use a donut-shaped ring magnet with a clinically increasing magnetic field. These machines have in practice been limited by the large radiative losses suffered by the electrons moving at nearly the speed of light in a relatively small radius orbit. Linear accelerator. They are often used to provide an initial low energy kick to particles before they are injected into the circular accelerators. Linear high energy accelerators use a linear array of plates to which an alternating high energy field is applied. As particles approach a plate, they pass through a plate, change their polarities, so that the plate now repels them and they are now accelerated by it towards the next plate. As the particles approach the speed of light, the switching rate of the electric fields becomes so high that they operate at radio frequencies. Linear accelerators are also widely used in medicine for radiotherapy and radiosurgery. Medical grade linacs accelerate electrons using a klystron and a complex bending magnet arrangement which produces a beam of 6 to 30 mega electron volts energy. Cyclotron also comes under cyclic RF accelerators, and we will discuss about it briefly in next slide. But now we will see about RF accelerators. Cyclic RF accelerators. The advantage of circular accelerators over linear accelerators is that the ring topologically allows continuous acceleration as the particle can transist indefinitely. When any charged particle is accelerated, it emits electromagnetic radiation and secondary emissions. As a particle traveling in a circle is always accelerating towards the center of the circle, it continuously radiates towards the tangent of the circle. This radiation is called synchrotron light and depends highly on the mass of the accelerating particle. Depending on the energy and the particle being accelerated, circular accelerators suffer a disadvantage in that the particles emit synchrotron radiation. As the energy increases, the particle speed approaches the speed of light as a limit but never attains it. Therefore, particle physicists do not generally think it in terms of speed but rather in terms of a particle's energy or momentum, usually measured in electron volts eV. Cyclotron. It was the earliest operational circular accelerators invented in 1929 by Ernest Lawrence. It is a characteristic property of charged particles in a uniform and constant magnetic field B that they orbit with a constant period at a frequency called the cyclotron frequency. The accelerating disk of a cyclotron can be driven at a constant frequency by a radio frequency accelerating power source. The particles are injected in the center of the magnet and are extracted at the outer edge at their maximum energy. Simple cyclotrons can accelerate protons only to an energy of around 15 million electron volts because the protons get out of the phase with the driving electric field. Isochronous cyclotron is the PSI ring cyclotron in Switzerland, which provides protons at the energy of 590 mega electron volts. Last but not least, black hole production is also one of the interesting topic and it is related to particle accelerator. Black hole production. In the future, the possibility of a black hole production at the highest energy accelerators may arise. The various possible dangerous scenarios have been assessed as presenting no conceivable danger. In the latest risk assessment produced by the LHC Safety Assessment Group, T has been argued that to conserve energy and momentum, any black holes created in a collision between UHCCR and local matter will necessarily be produced moving at the relativistic speed with respect to the Earth. While black holes produced in colliders will have some chance of having a velocity less than Earth escape velocity 11.2 km per second and will be liable to capture and subsequent growth. Thus, if stable microblack holes should be produced, they must grow far too slowly to cause any noticeable macroscopic effects within the natural lifetime of the solar system. Finally, we will discuss about some interesting facts regarding particle accelerator. There are more than 30,000 accelerators in operation around the world. One of the longest modern buildings in the world was built for a particle accelerator. Particle accelerators are the closest things we have to time machines, according to Stephen Hawking. The highest temperature recorded by a man-made device was achieved in a particle accelerator. The inside of the Large Hadron Collider is colder than outer space. Nature produces particle accelerators much more powerful than anything made on Earth. Particle accelerators do not just accelerate particles, they also make them more massive. The diameter of the first circular accelerator was shorter than 5 inches. The diameter of the Large Hadron Collider is more than 5 miles. In the 1970s, scientists at Fermi National Accelerator Laboratory employed a ferret named Felicia to clean accelerator paths. Particle accelerators show up in unlikely places.